Welcome back. We've been learning about hash tables, and in this lesson you're going to create a simple hash table in Python. First we're going to make an empty hash table, then add number values, then amend the program so that we can add text values, and we'll look at the issue of collisions and rehashing. First of all, we're going to make an empty hash table. If you're my student, then you can simply download the program that I've provided on the Moodle. If not, you can copy the code which I'm about to show you. The starter program that I have provided is called Hashtable Starter Program. So find that on the Moodle and look through it. You can pause this video now while you do that. This is what the file should look like on your screen. If you're not my student, you can pause the video now and type in this code. Have a look at what the Python commands say. The first part creates a list of 100 empty strings. This is what we're going to use as our hash table. And I've included some commands to print it out so that you can see what it looks like. The next part of the code that I've provided simply allows you to input numbers which are converted into integers. We haven't yet written the code to add these values to the table. So now we're going to work together to add code to the program so that the integer values are inserted into the hash table at the correct position. Remember that in a hash table, the location used for storage is derived from the stored data value, and this is called hashing. So we're going to insert data into the table at a position indicated by the data value itself. In this example, the data value is called number, so I'm simply going to use the integer number to tell me the location to store the value. So I added some very simple code. I've taken the number that the user has input and I'm using that as the index value in the array. So if I enter the number 5, it'll be stored at location 5. If I enter the number 80, it will be stored at location 80, and so on. So why not try that, make and run that code? And I expect if you're ahead of me, you can think straight away of something that could go wrong. So if you already know, perhaps you could think of how we could avoid that problem. Did you anticipate what the problem was going to be? Our user can enter any number of any kind, and the hash table has 100 locations. What if the data value they enter is a number bigger than 100? So if they enter 80, then their value will be stored at location 80. But if they enter 880, then that will cause the program to crash. So our hash table program certainly isn't completed yet. Can you think of a solution? I'm going to show it on the next slide, so have a little think about that. The answer, one possible answer, seems to be the best one, is to use the mod or remainder command. Remember what that does is it carries out an integer division and returns the remainder after the division. If we divide the number value entered by the user by the number of locations and take the remainder as the hash value, that will avoid the problem of numbers that are larger than the size of the hash table. Let's have a look at an example. Here I've got 6 memory locations. Of course, in real life, I'd always have far more than that. 6 memory locations. Find the hash value for the numbers 12, 1004 and 99. So let's see how that would work. First of all, let's take the number 12. 12 divided by 6 is 2 remainder 0, so we store this data in location 0. 1004 divided by 6 is 167 remainder 2. The first number doesn't matter, it's only the remainder that we need. So 1004 is stored in location 2. And finally 99 divided by 6 is 16 remainder 3. So 99 goes there. So it doesn't matter how large our numbers are, as long as we can divide them by the number of storage locations and take the remainder. So let's make that happen now. In our program, take the remainder when we divide the number that the user has entered by the size of the hash table. Remember that the percent symbol in Python is used to take the remainder. So why not try making and running this code, and you'll find that however large the numbers are that you enter, they will still find a place in the hash table. So I'm going to leave you with this activity for now. Create an empty list of 100 places, insert integer values into the list, deriving the storage location from the data value. And this is a very simple example of hashing. You may have been following along as I spoke. If not, pause the video now and carry out this activity. But what if the data that we want to enter into the table is a non-integer value? Can we manage to hash that type of data? Remember that we need to derive the location, and the location is an integer, from the original input data value. Can you think how you would do that with text data? I'll show you on the next slide. The answer is to use the ASCII number or Unicode number. It comes to the same thing. So get the ASCII number of each character in your string, and then, for example, add the ASCII numbers together, and that will give you the number value that you can use. To do this, we'll use a Python function called ORD, O-R-D. The ORD function takes any character as its parameter and returns the ASCII value of that character. So, for example, we can convert any letter into an integer value. Letter and value are identifiers of two variables. So this command in my program will convert a letter, a character of text, into an integer value. So change the top of the code so that we enter a text value rather than an integer, and I've called the identifier text. Then I've created a variable called total, and for every item, for every character in the text, I'm finding the ASCII integer value and adding it to the total. This is probably the simplest way to derive an integer value from a text string. And then I'm using the total as my hashing value. I'm getting the remainder and using that as the index number in my hash table. So I'm inputting some text and I'm converting that text into an integer. So have a go at that now. Here's the activity that I'm leaving you with. Amend the simple hash table program that you created before so that the user can input text values, convert these text values into integers, and use the integers as the storage locations. So this should work relatively well, but there's still the problem of collisions. In this section, I'm going to show you how to cope with the problem of collisions in the hash table. If two data items generate the same hash value, then the computer will try to store them both in the same storage location. Potentially one data value will overwrite the other. This is called a collision, and the smaller the hash table is, the more likely you are to have collisions. So let's look at an example. Here, as before, I've got 6 memory locations, and I've already stored the numbers 12, 1004 and 99. Now let's say I wanted to store the number 200. 200 divided by 6 is 33 remainder 2. So that should go into location 2 in the hash table. But there's a value there already. In order to avoid overwriting the value that's there already, I have to use a second algorithm to find an empty space for my data value. In this case, it's just counted down to find the next available empty space. The name for this is rehashing. So we carry out our ordinary hashing algorithm, but if we end up with a collision, we have to start a second algorithm called the rehashing algorithm. For example, a very simple rehashing algorithm would simply look through the list until it finds an empty memory location and store the data there. And that's the very simple version that we'll use in this demo program. So I've added this code to my program. If and while the storage location is not an empty string, so if and while there is any data in that storage location, I will simply count on by 1 to the next storage location, and that will give me the place to store my data. So amend the hash table program to add this rehashing code to avoid collisions. There are still a couple of further issues that we can address, but let's look back at what we've done so far. In this lesson, I've shown you the code to make an empty hash table, to add integer values, and then we've amended that so that we can add text values. Basically any values that can be represented in character form can be stored in our table. And we've looked at how to address collisions by using a rehashing algorithm. If you haven't done so already, make this code now. In the final slide, I'll give you some extra ideas for activities. So I'll leave you with some ideas for extending the hashing and rehashing algorithms. I'm not going to show you this code, so I'll just leave this up to you. Many hashing algorithms don't simply add up the ASCII values of the characters, they multiply each ASCII value by the position of the character in the string as you're counting through the string using the for loop. The reason for this is if two values are anagrams of each other, in the old system they would end up with exactly the same hash value, and that would cause more collisions. By doing multiplication like this, you prevent collisions. When you're doing the rehashing algorithm and counting through the array until you find an empty space, you could hit the end of the array because we're simply adding 1 to I each time. So if you reach the end of the array, reset I to 0. And many rehashing algorithms, instead of counting ahead by adding 1 to I, they add 3 to I. The purpose of this is sometimes you get a cluster of values in the same position in the hash table, and by adding 3 you quickly jump ahead out of that sort of collision zone. Anyway, these are ideas for more expert programmers to just have a go on their own. In the next presentation, I'll show you how to add code so that we can find the values that we want in the hash table that we've made. Okay, so I'll see you then. Bye for now.